Hello everyone, this is Nash. Today I would like to show you how to solve the theoretical problem, the problem 1 of EuPhO in 2022. And the problem is we are going to put a cylinder inside a beaker. And what is more, the cross-section area for the beaker is only a little bit larger than that of the cylinder. So this situation is quite different from the normal situation. The normal situation is we would like to put a cylinder on a big enough pool like the swimming pool. So when your cylinder is trying to oscillate and the water surface does not change at all. But now, since the cross-section area of the beaker is only a little bit larger than that of the cylinder, so when your cylinder is trying to oscillate, and so is the water surface. So I cannot just focus on the forces acting on the cylinder, but I also need to analyze all the possible forces acting on the water column in the gap between the cylinder and the wall of the beaker. Okay, so the problem is we want to find the period of the motion. Usually when the problem is trying to ask you the period of time, more than 99% it should be simple harmonic motion. But in order to characterize whether it is simple harmonic motion, we need to find out the relationship between the restoring force and the position away from its equilibrium points. So let's say it is at its equilibrium point, and according to the problem say the ratio between the density of the cylinder and that of the liquid is gamma, and the gamma is 0.7. Okay, you can imagine the liquid is water. I'll just call it water. That will be much easier. Okay, and so if the density of the liquid of water is rho, and so the density of the cylinder will be the rho times the gamma. So for the portion, for the height down below the water surface is gamma times h, and the h is the height of the cylinder. So imagine if I'm now displace the cylinder downward a little bit away from its equilibrium point by distance x1, So here will be x1 as well. And the water surface is gonna rise as well. So let's say the distance, the water surface away from its original position is x2. First, I want to find out the relationship between x1 and x2. And thanks to the continuity, we know that the change in volume provided by the cylinder will also be equal to the change in volume of the liquid. So the first step is the cross-sectional of the cylinder S and times the distance away from its equilibrium point x1, and it should be equal to the change of the liquid. Think about it, if the liquid trying to move back to its original position, and the change in volume will be the cross-section area of the liquid surface, which is the capital S, the base area of the beaker, minus the cross-sectional area of the cylinder, and times the distance x2. This is based on the continuity law. It's like a little bit like the conservation of volume. Okay, and this equation does not just fit for x1 and x2. If the x1 and x2 is position and the distance away from its equilibrium point, let's just take the derivative of the position, and it turns out to be the velocity. And let's just differentiate the velocity one more time. It turns out to be the acceleration. So with this equation, I does not only know the relationship between x1 and x2, I can also plug a1 for x1 and plug a2 for x2. This equation also fit for x, not only for x, but also for acceleration. So in order to characterize whether it is SHM or not, I need to find out the relationship between the restoring force and x1. The restoring force, according to Newton's second law, it is mass times acceleration. So that means I need to find out the linear dependence of A1. A1 means the size of the restoring force of the cylinder in x1. If there's a linear dependence, a linear relationship between A1 and x1, it is simple harmonic motion. That is our main goal. So I'm going to analyze all the forces acting on my cylinder. Okay, first is the force generated by the pressure difference. by the difference of the pressure. Let's say the pressure on the top is P naught and the pressure down below is P. So the pressure difference is going to pointing upwards. That is P minus P naught and times the cross-section area. That will be the part of the restoring force, and minus the gravity. The gravity is mg, and now the mass is equal to density and times the volume. Density times the volume. And what is the volume? The volume is the cross-section area S and times its height. So the gravity is the rho times S times h. This is the volume and times g. And turns out to be the gravity. And based on Newton's second law, this is equal to ma. Mass is equal to the density times the volume, and the volume is sh. This is mass. And mass times its acceleration is the net force. Okay, this is based on Newton's second law. Okay, but here is a little bit more complicated than normal situation, because I cannot just focus on the cylinder, but I also need to analyze all the forces of the pressure difference acting on the water column. The water column in the gap between the cylinder and the wall of the beaker. Because when your cylinder is trying to accelerate upwards with A1, and so is the surface, so is the water column. The water column is also trying to accelerate downwards. And I can say the relationship between A1 and A2 is so much like the relationship between X1 and X2, because acceleration is the second order derivative of the position. So equation 1 can not only tell me that the relationship between the X1 and X2, but also the relationship between A1 and A2. Okay, so are you ready to analyze the force acting on the water column? Ready? Okay. First, there will be gravity of the water column, and there will also be the pressure difference from the bottom and the top, from the bottom and the top. So let's say the direction pointing downwards is now positive direction. So the pressure the pressure difference acting on the water column should be P naught and minus P. P naught minus P. Okay, of course, I should this term, the P naught times the P naught minus P, should be multiplied by the cross-section area of the water surface. But I want to make my calculation clean, so I'm going to talk about the force per area. The force per area. Okay, the force per area. What is the force per area? That is the pressure. So I can only just analyze the pressure, because I'm only talking about the force per area. The force per area. The force per area. So I will make my calculation clean. Because the second term should minus the gravity, and the gravity is mg. And the mass is rho times the volume. And now the rho Vg is divided by the cross-section area. So the volume V turns out to be the height of the water column. So rho Vg is rho times height and times g, which is rho times g and times the height, the x1 plus x2 and plus the gamma h. This is minus. Okay, this is the force pointing downwards generated by the pressure difference, and minus, plus, okay, plus the gravity pointing downwards. That's all the forces acting on the water column, and based on Newton's law, it is equal to mass times acceleration, and the mass is now divided by the cross-section area. So the rho times V is the mass. But the rho times V should be written as the rho times the height, since I divide this term by its cross-section area. So it's rho times the height, x1 plus x2 and plus gamma h. This is something like the mass, and times its acceleration of the water column, A2. Okay, now I got three equations: equation 1, equation 2, and equation 3. So let me remind you, what is our main purpose? Our main purpose is trying to find out the period of time of this motion. And usually, if the problem try to ask you the period of time, then they got a lot of chance to be the simple harmonic motion. If we want to say this is simple harmonic motion, then you need to find out the linear dependence between the restoring force and the distance away from its equilibrium point. And the restoring force, the size of the restoring force, can be denoted as the size of the acceleration. So if I can find out the relationship between the A1, the acceleration of the cylinder, and x1, the distance away from its equilibrium point, which is like the amplitude. Amplitude is the distance between the equilibrium point and the end point. If this is simple harmonic motion, then the x1 should be the amplitude. If I can find out the linear dependence between A1 and x1, then I can conclude, I can claim that this motion is definitely simple harmonic motion. Okay, so let's just simplify all these terrible equations. First, I don't know too much about the pressure difference. I don't know too much about the pressure difference, the P minus P naught. I don't know about that. Okay, so the first thing is I want to replace the P minus P naught by equation 3. I'm gonna plot equation 3 back to equation 2 and replace the P minus P naught. I'm gonna switch P naught minus P, and this term on the right hand side, I'm gonna switch them and plot that back to this term. And don't forget, here's an S, the cross-sectional area of the cylinder. So it turns out to be okay, this is our first term, the rho times G times x1 plus x2 plus gamma h, and times what? Times s, don't forget the s. And minus this term, and minus rho, gonna be multiplied by s, rho s, and times x1 plus x2 plus gamma h, and times a2. Okay, and don't forget this term, the rho shg minus rho shg. The equation 2 is gonna be like this one, and on the right hand side is rho sha1, which is equal to rho sh m times a1. Done. Please help me check this equation. Did I make any mistake? S, okay, minus rho shg, correct. Rho sha1, okay, correct. Let's keep simplifying this. Simply by observing this equation, we know that all those terms, they all got rho s. So I'm going to cancel the rho s, the rho s, the rho s, the rho s, and the rho s. Okay. And what is more, this is minus shg. S, okay, oh, this is gh. The rho s has already been cancelled, the gh. And, oh yeah, I just made a mistake. Since the rho means the density of the liquid, the rho is the density of the liquid, and the density of the cylinder is gamma times rho, So I just forget the gamma. I forget the gamma. Okay, just plug that in. So let me just correct it a little bit. I should place the gamma right here. Here should be a gamma, and here should be a gamma. Okay, done. So let's just check it again. So this is G times gamma times H. This is G times gamma times H. So I can also cancel these two terms because this is minus. I can cancel the G gamma H and the G gamma H. I can cancel this term. No problem. So what we are left with is, I'm going to write it down right here. What we are left with is the G times x1 plus x2 and a minus, okay, check this term. This is x1 plus x2 and plus gamma h. I remember in this problem, it tells me that the liquid level oscillation is around 1 millimeter. 1 millimeter is 0.1 centimeter. And compare with the size of the height, since if this motion is simple harmonic motion, then the x sometimes should be really small. So compared the size of x between x and the gamma h, the x1 and x2 is relatively too small to be ignored. So I can fairly cancel these two terms. I can simplify this equation by doing this. So I don't need to write the x1 and x2 anymore. So it turns out to be gamma h times a2, gamma h and times a2. And this is equal to the gamma h times a1, the gamma h and times a1. So just rearrange it. I'm going to put the a1 and a2 together. So the g times x1 and plus x2 is equal to gamma h a1 plus a2. Okay. What we are looking for is the linear dependence between the restoring force and the distance away from its equilibrium point of the cylinder. So I want to find out the relationship of A1 and X1. And what I don't want to say is the X2 and A2. And thanks to equation 1, I can know the relationship between X1 and X2, because the X1 can be written as the x2 can be written as a lowercase s divided by the capital S minus s m times x1 times x1. And this equation does not only fit for x, but also fit for a2 and a1. So I can plot this equation back to this calculation. I can plot the back. I can plot that, plot the back. Keep simplifying this, okay? And it turns out to be g times x1 m times 1 plus lower s divided by capital S minus s is equal to gamma h and times 1 plus s divided by capital S minus s and times a1. Okay, what we are left with is the x1 and a1. This is what I'm trying to look for. And they'll get the 1 minus the s term. I can cancel this. I could cancel this. So finally, the a1, the acceleration of the cylinder, is g divided by gamma h m times x1. The acceleration of the cylinder means the size of the restoring force. And the restoring force gets some linear dependence. They are linearly dependent on each other. So I can say this equation is definitely simple harmonic motion. So if it is simple harmonic motion, it can be also written as the r, and the r is now the x1. The x1 is the distance away from its equilibrium point. It's the distance between the equilibrium point and endpoint, and that is the amplitude. So the acceleration can be also written as the x1 times omega squared. And let's just cancel the x1, and you can know that the omega is the square root of g divided by gamma h, right? The omega is the square root of g divided by gamma h. Well, with this omega, we can know that the t is 2 pi divided by the omega, because the omega is the angular frequency, and the angular frequency means the angle it can change per time. The angle it can change per time. And 2 pi is the angle for a whole circle. So the 2 pi divided by omega, it means how much time you should take to complete a whole circle, which is the period of time. So the period of time is 2 pi times the square root gamma h divided by g. Okay, done. But this problem needs you to calculate the exact value. 2 pi, no problem, is a constant, and the gamma is 0.7, and h is 10 centimeters. 10 centimeters means 0.1 meters, and for g is 9.8, no problem. So you plug all those constants back to the final result. We can note that the period of time is around 0.53 seconds. Okay, done. So this is the theoretical problem, the problem 1 of EuPhO, the 6th EuPhO in 2022. So if you're interested, please let me know. In the future, I will be glad to show you how to solve problem 2 or 3. Okay. Thanks for watching, and this is Nash.